Let's review a few things we learned in the last video. We said that if we had an elementary matrix, that's type 1, then the determinant of that matrix is -1. We said that if we had a matrix E that was type 2, then the determinant of that matrix is some scalar, alpha, that corresponds to the row that you multiply the identity matrix by, which we call alpha. If E is a type 3 elementary matrix, then the determinant is just 1. We also learned that if we take the determinant of an elementary matrix times any other matrix, that's n by n, then this is equal to the determinant of that elementary matrix times the determinant of the matrix A. And finally, we said that a matrix A is non-singular, meaning it's invertible, if and only if the determinant of A is not equal to 0. And in other words, if A is singular, then the determinant of A is going to be 0. Let's talk about some important properties of determinants. So suppose A and B are two n by n matrices. The first one we've already gone over. The matrix A is non-singular if and only if the determinant of A is not equal to 0. Remember, non-singular means invertible. The second property is that if we take the transpose of a matrix and find its determinant, well, that's going to be equal to the determinant of the original matrix. And the last property, which you'll probably use a lot, is that the determinant of two matrices multiplied together is the same thing as the determinant of each matrix multiplied together. This one's interesting because here A is not just an elementary matrix. This is any matrix. So recall, I want to add for this last property that if we multiply two matrices together, well, they're not commutative. So A times B is not equal to B times A. However, the determinant of A times B is equal to the determinant of B times A. And you can see that just from right here if we use this property. Now these are real numbers. So this might be like a 3 and this is a 5. So 3 times 5 is the same thing as 5 times 3. So you can rewrite this This is equal to the determinant of B times the determinant of A, which is the determinant of B times A. It's very interesting. The two matrices, when we multiply them together, if we do A times B, it's not going to be equal to B times A, but the determinants of whatever matrices we get will be the same. I'm going to prove one of these. By the way, you should memorize this one. I'm actually going to prove the second one. And we're going to prove this by induction. So if you've never seen an induction proof, this is a good time to learn it. So this is proof of number 2 by induction. So when you want to prove something by induction, you have something called a base case, and then you have an induction step. So we want to prove that for any n by n matrix, that the determinant of A transpose is equal to the determinant of A. So let's write that statement. This is for any n. So the base case is the smallest case we can come up with. Let's say A is a 1 by 1 matrix. So A is equal to, let's just say, A11. Well, then A transpose is also A11. And you can see that A is equal to is transpose, but the determinant of A is A11, which is also the determinant of A transpose. This is the smallest base case we can show, but I also want to show you that it's true for a 2 by 2 matrix, just as an extra step. If A is 2 by 2, so let's say it's A11, A12, A21, A22, where these numbers are real numbers, then A transpose is A11, A21, A12, A22. And let's find the determinants. Looking at this one is A11, A22 minus A12, A21. And then the determinant of A transpose is A11, A22 minus A21, A12. So you can see that these are equal. You could continue this, you could say, show it for the 3 by 3 case as well. But what you do, once you have your base case, which is the smallest number you can use, which is n is equal to 1, we're going to assume it's true for some number k. So that's going to be the induction step. So what we're going to do is we're going to assume the determinant of A is equal to the determinant of A transpose for some n is equal to k. We will show that the determinant of A is equal to the determinant of A transpose for n is equal to k plus 1. So we're going one step up. So if A was a 2 by 2 matrix, we're assuming it's true for the 2 by 2 matrix, which we've already shown it's true, and now we're going to show it for the next one up, so a 3 by 3 matrix. If A is a 10 by 10 matrix, we're assuming it's true for the 10 by 10 matrix, and we're going to show it is true for the 11 by 11 matrix. That way you're making a step. Since we've already shown it was true for the 2 by 2 case, then we're showing it's true for the 3 by 3 case. And then we can show it's true for the 4 by 4 case, and so on. Okay, so let's find the determinant of A and show that this is equal to the determinant of A transpose when A is a k plus 1 by k plus 1 matrix. So I'm going to kind of write out what I expect A to look like. So A is A11, A12, A13, all the way to A1 k plus 1, then A21, A22, A23, A2 k plus 1, and we continue this like so. And now I want to take the transpose, just so I can visualize it. So let's write down here what the transpose is. Well, it's A11, A21, A31, and so on until you get to AK plus 1, 1. And then this side is going to be A12, A13, and so on until you get to A1, K plus 1. Just to write out some more stuff here. And since we want to show that these determinants are equal, well, let's actually take the determinant of both of these. I'm going to start with the determinant of A. So what I'm going to do is I'm going to pick a row to go down. I'm going to pick this very first row, and you can pick any row you want or a column. It's going to be a similar proof. So the determinant of A, well, let's write this out. This is the sum from j is equal to 1 to k plus 1 of A1j, negative 1 to the 1 plus j, m1j. Now let's review what this means. Now this is a sum. There's going to be k plus 1 terms in the sum. We've talked about this before. We start with this one, A11, we take negative 1 to the 1 plus 1, and then we mark out this row in this column, and this matrix is the minor matrix, and that's called M11. And then we move to the next entry in this row, which is A12. Then we do negative 1 to the 1 plus 2, and then take the minor matrix, which consists of this column and the rest of this. Okay? So this is the determinant of A, going along this particular row. Now let's compare that with the determinant of A transpose. Well, what I'm going to do is I'm going to go along this column. So we get that the determinant of A transpose is the sum j is equal to 1 to k plus 1. So what would this look like? We have, notice the one that is changing is going to be the back one. So this is A1j to the negative 1 plus j. And then the minor matrix is right here. And this minor matrix, let's compare it to the original minor matrix. So when we marked out the first row and column, what is the difference between this one and this one? Well, if this one is M11, this one is M11 transpose. So what I should write here, sorry, I should put determinant of Mij, so let's fix that. Determinant. So I'm going to put determinant of M1j transpose. Okay, but M1j, the matrix M1j, is an k by k matrix. So let me actually, I want to put this lower down so I can put them both together. Okay. So since Mij is k by k, it's a k by k matrix, then the determinant of Mij is equal to the determinant of Mij transpose. That was what we assumed. We assumed for any k by k matrix that the determinant of such a matrix is equal to the determinant of its transpose. So what we can do now is we can substitute, instead of this determinant of Mij transpose, what we're going to put is that this is equal to, just repeat all of this, this 1j, negative 1 to the 1 plus j, determinant of Mij. And now you can see that this is the same thing as this. So now we have proven that the determinant of A is equal to the determinant of A transpose for n is equal to k plus 1. And now we're done. So since when you do the inductive step, you get that this implies the determinant of A is equal to the determinant of A transpose for all n, where A is an n by n matrix. So that's what the n stands for. This goes with the size of the matrix. Okay, let's move on. I want to do a few exercises involving some of these properties of transposes and determinants. All right, the first one is, here I have a matrix A that is a 3 by 3 matrix, and I want to know the determinant, and I want to figure it out without actually having to use that formula for the determinant. I want to involve elementary matrices. But of course you can find the determinant of this matrix. It's pretty simple. So let's look at this matrix. We know that if we have an upper triangular, I'm going to write it like this, matrix, or a lower triangular matrix, then the determinant of such a matrix is the product of the diagonal entries. This matrix that I have written here, it's not upper or lower triangular. Notice that it's not upper because I have a 2 here, not a 0. But it's pretty close to being upper. In fact, the only thing I would have to do to make this matrix an upper triangular matrix is switch these 2 rows. So if I apply E, which is the type 1 elementary matrix, where I switch the second and third row, if I apply E to A, what will I get? Well, I'll have 1, 1, 1, 0, 2, 4, 0, 0, 5. And this is an upper triangular matrix. And what's the determinant of this matrix? Well, it's just 1 times 2 times 5, which is 10. But what I wanted to find was the determinant of the original matrix, A, right? What's the determinant of this matrix? So I need to find the determinant of A. Well, from what we've learned, this is the same thing as the determinant of E times the determinant of A. So let's write that down. And we know that the determinant of E times A is 10. So we get that this left-hand side is 10. And E is an elementary matrix, a type 1 elementary matrix, right? Because we switched 2 rows, and we know that a type 1 elementary matrix, its determinant is -1. So that tells us that the determinant of A is -10, just by dividing both sides by -1. Interesting. Let's look back at this matrix. Something we could do is we could actually figure out what the determinant of this matrix is using the determinant formula. And what I would do is I would go along this row here, and the determinant of A would be 0 plus 0 plus 5 times -1. This is the 2, 3 entry, so 2 plus 3. And then we cross out this row in this column, and we take the determinant of this 2 by 2 matrix. So we get, this is -1 to the 5th, so this is -5 times 2 minus 0, which is indeed -10. So I don't know which one you think is easier, but it just gives you another option to finding the determinant. Let's try another one. So this one, again, we can find the determinant like normal, but let's see if we can multiply by an elementary matrix or more than one elementary matrix. Well, what I'm going to do for this matrix, you can pause it and you can pause this video and think about it for a second, and then see if you can come up with a way to get this matrix maybe into upper or lower triangular form. Okay, what I'm going to do is I'm actually going to subtract row 1 from row 2. So I get that this matrix, you can write it as, in fact, let's multiply it by -2, sorry. I'll get, so this is -2, -2, -2. I'll get 0, 0, 1, 0, 1, 3. And then I can switch these 2 rows. So now I get 1, 1, 1, 0, 1, 3, 0, 0, 1. And then I can see that this matrix, this new matrix, its determinant, let's call this matrix C. The determinant of C, because it's upper triangular, is 1 times 1 times 1, which is just 1. But we want to figure out the determinant of this matrix. So how did I get to C from B? Well, what I did was I multiplied on the left by 2 elementary matrices, because I had 2 steps. That is equal to C. What kind of elementary matrices are these? So the determinant of E2 times E1 times B is equal to the determinant of C, because they're equal. So then I get that this is equal to 1, and this is determinant E2, determinant of E1, and then determinant of B. Now I just need to figure out what kind of matrices these are. So E2, which is the one, so E1 is the first action we took on this matrix. So the very first thing we did was we multiplied by -2 and added it to the second row. So E1 corresponds to a type 3 elementary matrix, right? And a type 3 elementary matrix, we know its determinant is 1. For E2, this corresponded to switching 2 rows. And that type of matrix has determinant -1. So that tells me that the determinant of B is -1. Okay, you can double check this if you like. you can maybe go down this row here and see if you get the same answer. Let's move on to the next question. Suppose A is a 3 by 3 matrix and we know the determinant. So I'm not giving you the actual matrix, but I'm telling you what the determinant is. And I want to know, can you figure out the determinant of 3 times A? Well, let's see. What is 3 times A? A lot of people will make this mistake. They'll say the determinant of 3 times A is 3 times the determinant of A, which is 3 times 2, which is 6. This is not correct. Why is it not correct? What happens when you multiply a matrix by 3? So let's say you have the matrix 1, 1, 1, 2, 2, 2, 1, 1, 1. This is just a random matrix, and I multiply it by 3. Well, what's really happening is you're multiplying every single row by 3. So you get 3, 3, 3, 6, 6, 6, 3, 3, 3. When I multiply a single row by a number, that corresponds to an elementary matrix, right? So if I take a number and multiply every single row by this number, then I'm going to have 3 elementary matrices for this particular matrix because it's a 3 by 3 matrix. So E1 can be the matrix 3, 0, 0, 0, 1, 0, 0, 0, 1. E2 is 1, 0, 0, 0, 3, 0, 0, 0, 1. And then E3 is 1, 0, 0, 0, 1, 0, 0, 0, 3. And then from there, you can see that 3 times A is the same thing as E1 times E2 times E3 times A. So the determinant of 3 times A is equal to the determinant of E1 times the determinant of E2 times the determinant of E3 times the determinant of A. And we said in the very beginning that the determinant of A is 2. And these matrices are type 2 elementary matrices. So what we get is 3 times 3 times 3 times 2, which is equal to 27 times 2, which is 54. I bet you weren't thinking that. Can we generalize this? Yes. So what if we had a matrix A that's n by n, and we want to find, if we know the determinant of A, what is the determinant of 3 times A? Let's say that this is equal to 2. Well, this is equal to 3 to the n times the determinant of A, which is 3 to the n times 2. Because every single row will get a 3, so you would have n type 2 elementary matrices that all have a 3 with it. I think I have a couple more problems I want to look at. Let's say we have a matrix that when we square it, we get the identity matrix. Can we determine the determinant? Yes, we can. So what we want to know is, what is the determinant of A? Well, let's start by saying that the determinant of A squared is equal to the determinant of the identity matrix. What's the determinant of the identity matrix? Well, that's just equal to 1. Just the product of the diagonal entries. But the determinant of A squared is the same thing as the determinant of A times A. But here we have a product of 2 matrices, and now we can use that rule that says product split. And from here we can say that the determinant of A, well, we've got two of these. This is like x times x is 1. So here we have x squared is equal to 1. So we take the square root and we get that the determinant of A is plus or minus 1. So whenever you have a matrix that you square it and you get the identity, its determinant is always going to either be 1 or negative 1. I think this is the last, no, I got another one down there. All right, well, let's continue. Let's say we have that the determinant of A is negative 12, and let's say A is an invertible matrix. It's obviously invertible because the determinant is not 0. What is the determinant of A inverse? Well, this is going to be similar to the last problem. Maybe think about it for a second and see if you can figure out. Pause the video and then come back and see what I did. So we know that A times A inverse is the identity matrix. So then the determinant of A times A inverse is going to be the determinant of the identity. Well, the determinant of the identity is 1. And this side is the determinant of A times the determinant of A inverse. We know the determinant of A is negative 12. So from here we can say the determinant of A inverse is negative 1 over 12. These numbers, the inverse has to be the reciprocal in order for them to multiply together and get 1. This is kind of fun. Let's say we have two n by n matrices. Is the determinant of the sum of matrices equal to the determinant of each matrix and added together? This was not a property I listed under determinants. We had a property like this for multiplication, but not for addition. And there's a reason for that, because it's not true. How you can show that this is not true is by using a counterexample. You just need to find one example of a matrix plus another matrix where the determinant of the sum is not equal to the determinant of both of the matrices added together. So I would always try to pick something that's really easy. And the easiest example I can think of is the 2 by 2 matrices. And we're going to choose the identity matrix, which is 1, 0, 0, 1. I want to come up with two matrices that when I add them together, I get the identity matrix. Okay, so what I'm going to choose is A is equal to 1, 0, 0, 0, and B is equal to 0, 0, 0, 1. Notice that if I add these two together, A plus B is going to give me the identity matrix. Now let's take the determinant of both of them. So obviously the determinant of A plus B is going to be the determinant of the identity matrix, which is 1. Okay? Let's circle this. Now, let's see if the determinant of A plus the determinant of B is equal to 1. The determinant of A is 1 times 0 minus 0 times 0. That's 0. The determinant of B is also 0. 0 times 1 minus 0. And that shows us that the determinant of A plus the determinant of B is 0 plus 0, which is 0. So we can see that the determinant of A plus B is not equal to the determinant of A plus the determinant of B.